Okay, so let's see. So last time, so let me summarize quickly, then I'll tell you. I'll show you. So last time I explained, so this formula that nabla k is equal to this sum, which let's just call omega k. And so this is this giant sum of all these different factors. And then what I explained is that this is also equal to the Frobenius character of doubly graded SN representation with two different symmetric group actions, so one for each of the two variables. And I told you this was equal to the equivariant Borel-Moore homology of a certain space, which I think I defined, but didn't really have time to explain what it was. And so up to, let's say, up to a sign twist and a grading shift. It's equal to the equivariant Borel-Moore homology of a certain space I was calling y gamma k plus. And so what this space is the certain positive cone. And I'll give an example what I mean by positive cone. In the unramified affine Springer fiber, in type A. So this is a space studied by Goreski, Kotwitz, and McPherson in a paper which has the word unramified Springer fiber in the title. Or maybe it's Springer fibers in the unramified case. So instead of writing this again, let me give you an example and then show you how to connect it to that formula that I wrote down. So the affine Springer fiber, so let's take the case of n equals 2. So this is the same n that appears here. So I'm going to describe a space whose homology groups correspond to the nabla operator applied to E2 with that plathistically transformed E2 in two variables. And so what this Springer fiber looks like for n equals 2 is, first of all, there's infinitely many connected components, one for each positive integer. And that's because we're taking really the GLN version, whereas the SLN version is just like one of these integers worth of copies. And so what each one of these copies looks like is an also infinite chain of CP1s, or in other words, a Riemann sphere glued at the corners. So each one of these blobs is a different sphere, and then they're connected at each of those different points. So this is what this Springer fiber looks like for the case of n equals 2. Let's draw one more. And so what I mean by this positive cone, so let's say I'm going to draw the integer out here. So this is the copy for the integer like 0, 1, and -1. And all I mean by this positive cone thing, so this y subscript 2 plus, it looks like this. So let's do this. I'll use a different color. Okay, this red doesn't work. There, okay, red. And so what it looks like is, it's like this. So that's an example of the space whose Frobenius character is the thing that I'm looking at. And so what the variables Q and T correspond to, so the Frobenius character, it has to be an SN representation. So the SN representation is what is called the dot and star actions, which are also sometimes called the monodromy action and Springer action. And it's a doubly graded space. And so the first grading is just homological degree divided by 2. So that's the Q variable, and the T variable in this setup just labels the what connected component you're in. So this would contribute 1, this would contribute T, this would contribute T squared, etc. So for getting the SN action, so to give you, let's see, let's write this here. Yeah. Let's write it here. So in this example, nabla of E2 of xy over 1 minus q times 1 minus t. And so if I take this expression, so this is, so k is equal to 1. If I take this expression and I just forget the symmetric group character, which is to say I would take the coefficient of 1, 1, 1 in both the x and y variables. So by extracting that coefficient, I just ignore the SN action. And then I told you there was a sign twist and a grading shift. So there's a little q minus 1 out here. And so in fact, that's equal to the following power series. It's 1 over 1 minus q squared times 1 plus q inverse plus t times 1 plus 3 q inverse. So like you could check this on a computer, that this is what you get if you apply nabla to this E2, plathistically transformed E2. And so you just keep getting the, everything's the same except the coefficient in front of q inverse keeps growing. It's all the odd positive integers. And so now what you can compare is that, let's say the second term, t squared, this 1 plus 5 q inverse, that is in fact the Poincare polynomial of this space here, right? Because there's one connected component, so Betty 0, you have 1, but then there's these 5 spheres, and so you have 5 different contributions to Betty 2. You have five different voids, and so that 5, that's the same thing as this 5 that appears here. And so then modulo the SN action, which I'm suppressing, this is an example of how what you're computing. Does that make sense? Is there anything I can explain with this? I think this is sort of a nice, this is kind of the best example of the checking it against the homology calculation. Okay, so that's the example. So that's what this formula is really about. And so this what this combinatorial sum is it is basically counting with these sort of interesting automorphism factors. Remember from the formula from before, it's basically counting Schubert cells in this space. So it's counting, like it's counting these, in this case, these CP1s, and that's where the formula comes from. So now what I'd like to show you is starting with that formula. I can do all kinds of things to it. I can take this, take omega k, maybe I'll just write it again. And I can do all kinds of specializations to both the x and the y variables. Like I can do plethism, I can extract some coefficient. And what I want to do is show you what the interpretation of those things is in terms of this, terms of the homology groups of this space. So let's just write this down one more time. And by the way, in the notes, in the part about Borel-Moore homology, so there's a thing there about why this is sort of, it's negatively graded. You naturally negatively grade homology. And so there's a basis, you grade Borel-Moore homology is usually negatively graded. And so there's an example there in the flag variety. And so that's why it's a Q inverse that's, when you increase homological degree, that's why this Q is sort of going in the wrong direction. And since X to the A, Y to the B, Q to the div. Okay, so here's the first specialization. So this is, here's a corollary. Let's say I start with my thing omega k, and then I plethistically transform it. Well, actually, no, this one, not plethistically transforming it. I'm going to extract the coefficient of x to the 1 to up to n. So like all different variables, x1, x2, x3, x4, and then the coefficient of y 1, 1, 1, 1, 1. So I'm just taking coefficient of like y1 to the n. So in this case, what I get, because the x variables are all different, there is no automorphism factor. And so in fact, what I get is a formula for nabla k of p1 to the n, and the coefficient in the elementary symmetric function. And so this is what I get if I apply this specialization to the nabla expression. And then if I do this to omega of k, what I end up getting is a sum over integer, non-negative integer vectors of m, t to the size of m, and then q to the to some statistic, which let's just call d dk of m. And that's the result of taking div k with m, and then a is equal to 1, 2 up to n, and b is the composition 1, 1, 1. And so this is a formula from a well-known paper of Ben Elias and Matt Hogenkamp. And I forgot to put 1 over 1 minus q to the n. And it's also equal to the Hilbert series of Haymann's alternate ideal, which is generated by the diagonally anti-invariant symmetric functions over 2n variables. So that's one specialization. So if you apply that, you get what this thing turns into is this this well-known formula of Elias and Hogenkamp. So the second one, what happens if I do this plethism? So if I take omega k and I send it to omega k of x and y times 1 minus q. So this is the type of plethistic substitution that that comes up in the superization formula. So I substitute, I take the power sum pk and I evaluate that at pk of y times 1 minus q to the k times pk of y. And so in this case, what does this give me? Well, on the one hand, so it gives me a different interesting sum, which I can compute using the superization formula. But the meaning of this thing geometrically is that it's the usual, like, non-equivariant Borel-Moore homology of that same space. And so the reason for this is, so if I have a if I have a GKM space, and so this guy, this is a GKM space. In fact, if you choose the torus action correctly, so you're probably noticing it has infinitely many fixed points. So it's not lit quite. Technically, it's not a GKM space, like Sean pointed out last time. However, notice it's just a disjoint union of these finite guys, and so you can each space individually is a GKM space, and so you can calculate it using the calculate explicitly using the GKM relations. Anytime I have a space like that, one of the conditions is that it's equivariantly formal. And what that implies is that I can compute the usual equivariant cohomology, or on the other side, the usual equivariant Borel-Moore homology, by just tensoring out over the equivariant homology of a point, which is the same as C x1 up through xn, tensoring over that with just C. So setting all the x's equal to 0, and I recover the usual homology. Well, in terms of plethism, that's the same. That's also what plethism means, right? If I have the Frobenius character, then the plethistic substitution 1 minus q is just the Frobenius character of tensoring out over C of x1 xn with C. And so this tells me that, so combining all those things tells me that I'm getting this space. And so what you get is a interesting expression, which is actually just counting the Schubert cells. It's not an equivariant. It's different from the equivariant expression. And in fact, this is very close to a formula discovered by Andy Wilson earlier for nabla of En, I think I'm getting this right, of just x over 1 minus t. I believe that's the right form of that expression, right? So if I take y and I've evaluated at 1 minus q, that evaluation, it commutes past nabla because nabla is just happening in the x variables. And so all that does is it just removes that 1 over q factor. Not so if I did it in the x variables because it doesn't commute with nabla, but in the y variables, it just takes away that 1 minus q. So that's the meaning. So that's the first substitution. So here's the next one. What if I go one step further and also including a sign twist here? So the next substitution is I first do y goes to y times 1 minus q, though I'm actually going to do q minus 1. It's not much different. It's just a omega. But then after that, I'm going to do the substitution of x goes to x times t minus 1. So in other words, I'm going to start with that. So that would be starting with this formula. And then further going on to do a plethistic substitution in the x variables. So in this case, geometrically, it's a little harder to describe, though I will in a second. But in terms of symmetric functions, it's a thing which has the property that if I expand it into monomial symmetric functions in x and y, so the coefficients, let's call it a mu nu of qt, it has the property that a mu nu of qt equals 0 unless mu is smaller in dominance order than nu transpose. And the reason for this, the reason it has to be, is that if you look at the nabla expression, right? So what would this be? This would be like taking the composition of say it like this, xt minus 1 nabla of x over t minus 1 of en of just xy. Right, because because I eliminated the q minus 1 factor in y, and this substitution, x goes to x over t minus 1, would insert the denominator in xy. Then I would apply nabla in x, and then I'm coming in afterwards and evaluating the result at x goes to x times t minus 1. Well, but so this thing, right, so the nabla operator, though, is diagonal in the modified Macdonald basis. But the modified Macdonald basis basically comes from the usual Macdonald basis, which is triangular in the monomial symmetric functions, after taking the plethistic substitution of x goes to x times t minus 1. And so if I conjugate nabla by that, this whole thing is going to be triangular in the usual Macdonald basis. So the J basis. So therefore, it's diagonal in that basis. And so this operator is triangular in the monomial basis, or the Schur basis, either one, because those two are also triangular. So I have to get some expression where these coefficients vanish. And so why this is useful is, so this is the way proof 1 proceeds. Proof 1 of the formula. And so the way it goes is, you say, just take the candidate for the formula, take this big combinatorial sum. I know on the one hand that I have to, I take that sum, and if I check that after doing this plethistic substitution, I have to check combinatorially, and it's a kind of intricate argument. You have to count certain diagrams so that they cancel, and you show that the right-hand side of the formula satisfies this property. So once you have that, combine that with the fact that it must also end up being symmetric in the x and y variables. So once you establish those things, that proves that that expression must be the nabla operator, because you could use the triangularity, the symmetry, and the leading term, as you could take that as a definition of the nabla operator. And so that's the way proof number 1 proceeds, is you take these two different substitutions in the order first q minus 1 and then t minus 1. And by applying the superposition formula, you show you have this vanishing. So that's the hardest of the axioms to check. So that's what that substitution gets you. So here's the fourth thing. So I started to mention at the end of the first one, there's another way of writing this nabla k thing. So another way to write this expression, and so this is very straightforward, to take the sum and reduce it to this thing. If I collect the m and a terms, what I end up getting is something like t to the power of the size of m, q to dinv of m and a. So dinv of just two things is the same as you'd get by taking dim of n of a b and putting b is equal to 1, 1, 1, 1, 1 over the same automorphism factor, x to the a, but then you sort of collected terms in y, and you get the unicellular LLT polynomial of the y variables. And so what this thing is first of all, there's a mechanism which was sort of mentioned in the first lecture for taking one of these sorted pairs M and A and turning that into a Dick path procedure depending on K, which was the power of nabla. And basically it's just, it's what you think. You count the pairs that contribute to DINV, and those are the things under the path. Yeah, I think it's under the path, not over the path. And so this unicellular LLT polynomial. So on the one hand, this is the same one. It appears in the proof of the shuffle conjecture. But also we now know that this is the equivariant Borel-Moore homology. By results of Shereshian and Wax, and Guy Paquet and others, of the regular semi-simple Hessenberg variety. So we'll call this, regular semi-simple Hessenberg variety associated to pi k. So this is another example of a GKM space. This regular semi-simple Hessenberg variety. So you can compute it using the GKM relations. It also has the property that if I plothistically transform this by substituting y times 1 minus q, just like before, I get the usual Borel-Moore homology of the regular semi-simple Hessenberg. Whoops, for u, this should be a pi. And so this is Stanley's chromatic symmetric function. Stanley Stembridge, chi pi. And so this is the thing which is this is the subject of the e-positivity conjecture. So the statement that this guy, and I believe I'm missing an omega thing here, that this guy is e-positive. So these are all the same things. So this gives a LLT expansion of this nabla operator, and so also it gives a chromatic function expansion of this guy. So it gives if I apply that 1 minus q substitution, I get a chromatic symmetric function substitution of this guy. And so what does this mean geometrically? And so the answer, so the geometric meaning is a different paper by GKM, and it has to do with what's called the Hessenberg paving. Y gamma k. And so what this paving is if I go up to this space, what the paving does is it just kind of, oops, it's erasing the whole thing. I'll just draw it again. So basically what it's doing is, so the paving is writing this space as a disjoint union of affine bundles over regular semi-simple Hessenberg varieties. So by affine bundle, I just mean a complex vector bundle. So there's two types of Hessenberg variety in dimension n equals 2. there's two disjoint points, and then there's all of CP1. And so this paving writes this thing as a disjoint union. Let's go like this. Of this YK space into spaces which look like vector bundles over the Hessenberg variety. So for instance, the middle one is just a CP1. That's a simple Hessenberg variety with a trivial path. The next one is two copies of C, like disjoint union of C plus C disjoint union C. And that you can think of as a rank 1 vector bundle over just two distinct points. And so the rest of the factors are all just two distinct points, which is the other type of Hessenberg variety. And then the vector bundle over those, which is just one-dimensional vector bundle. And so that paving, it turns out that sum corresponds to this disjoint union. And so that disjoint union is what gives you this expansion. And so now I should point out this is also important because so this expansion, so like when I have a formula for like say omega k for the nabla operator or applied to some symmetric function, that expression is it's a quasi-symmetric expansion. And so you have to show that it is at least symmetric so that it's plausible. And so how does one do that for the sum that this omega k sum? And the answer is, well, you use this expression, right? So often the way it goes is you just say that if you want to show a quasi-symmetric expansion is actually symmetric, you might just express that in terms of LLT polynomials. And so this is that same sort of thing. So by writing this sum as an expansion in terms of these unicellular LLTs, I've in fact also proved that it's symmetric in the y variables. On the other hand, once I know that it's symmetric in switching x and y, which it is, then I've also shown that it's symmetric in the x variables. And so you actually have to use that like in the argument. So this is also how you just establish that it's symmetric. Okay, so I have there's two more. And the next one is something that's sort of so the next two I want to show you is how do I recover which specialization recovers the shuffle theorem. So this is a corollary of this is another proof of the shuffle theorem. And then the last one is on the one hand related to sign positivity of nabla, but also several other things, and there's a lot of sort of open questions with it. But the sixth one is, let's say I take this omega k, and so now I do the evaluation of y is 1 minus q and then times 1 minus t. So this is different from the previous one. So the first one was just y goes to y times 1 minus q. The next one is in what if I then substitute x goes to x times 1 minus t. This one is what if I substitute y goes to 1 minus q and then substitute again y goes to y of 1 minus t. And so in this case, I'm getting a formula for nabla k of nabla k of just en of xy, which is the same thing as nabla k of the sum over mu of S mu by the Cauchy product, then S mu conjugate over y. Right. See, if I take the original expression nabla applied to the plathistically transformed en, and if I do this plethistic substitution in the y variables, the substitution in the y variables commutes with applying nabla in the x variables. So I can just pull it in front of nabla, and all it does is it just removes the transformation. And so these would be giving you the coordinates, or these would be giving you the coefficients of nabla applied to the Cauchy product. And so now what I'm saying is, if you start with the expression we had for omega of x and y1 minus q, take that formula and now just apply the superization formula with the t variables. So for the plethistic substitution in the t variables, and you work with that formula and you do some combinatorics, you will get the formula for the usual shuffle conjecture. So not directly the compositional one, but the usual one. And so just to show you what this means algebraically. So if I take the module description I had, so this was the explicit module, which is a presentation for that equivariant Borel-Moore homology, right? So this was this polygraph type module of the the sort that appears in Mark Hayman's polygraph theory, right? So it's this thing in 4 variables. And so now the statement is, if I take M and I tensor it over the polynomials in 2n variables with C, so C is thought of as C of xy modulo the maximal ideal generated by those all the x variables and all the y variables. So in other words, C is the module over CXY where everything acts by 0. In fact, this is the diagonal coinvariant algebra. Right, and so that every time you do a plethism, that's like taking the derived tensor product with C. And so the sort of the 0th level of this derived tensor product, which is really a Tor group. This is in fact this is just the usual tensor product. And so from this, you're actually getting the Frobenius character of DRN. So that's how that connects. And so the last thing I want to show you is the 7th specialization. And this is one which has some interesting quasi-symmetric functions, which I wanted to show you, which have some very interesting properties, only some of which are proved. And so that's the following thing. So let's say I start with omega k of xy. There's 2 specializations I can do. So let's say I take the specializations I was looking at. In the last part. So the first thing is just the result of tensoring out over the little x variables in M. So this module M, so something that always seems to happen with these polygraph modules is that they're not free over the x and y variables, but they are free over just one set of variables. So in terms of equivariant homology, this makes a lot of sense. It's the statement that GKM spaces are free. So you can, yeah. So it makes geometrically, it makes a lot of sense from that side. But once I've tensored out, by those x variables, it's no longer free in the remaining y variables. And so this would have to be interpreted as a sort of Tor groups. In the little y variables. But now I can ask, what if I do this? I mean, I can do this in either order. So I could also have done plethism in the t variables first in the on the y side. So this would be M tensor over C of y, let's see. And then I could take derived tensor product over C of x. I have to get the same thing, but I'm going to get a very different expression for this same thing, which is equal to nabla k of En of xy. And so what is the next question is, what is the geometric meaning of this guy? And what sort of expressions do I get if I calculate this thing at the bottom, but by doing the plethisms in the opposite order? So the statement is that, and so this is in follow-up paper called GKM spaces. Signed positivity of nabla. And so this is an expression for En of xy over 1 minus q. So on the one hand, this expression, it has to equal the same thing we had from the same as number 2, same as 2, just with the x and y variables interchanged, because the whole thing is symmetric. So this will be a different formula that equals this, just substituting q and t. However, it's going to be a very different expression. I mean, in part because the QT symmetry is always like that. And so what this equals is this is the equivariant Borel-Moore homology. So it's still equivariant, it's not the non-equivariant, but of a space which is a fundamental domain for the space level action of a lattice on y of gamma k. And so let's call this UK. And so what this thing is so this is it's an open subset. There's this lattice action, which I haven't really mentioned, is that on this Springer fiber, there's a space level action of z to the n. And its induced action on homology is like multiplication by the y variables. So the y variables actually they come from a space level action. And this was studied by GKM in the unramified paper, in the case of more general root systems. And so this space, it's UK, it's not equivariantly formal. If it were, I wouldn't have to say Tor here, I could just say tensor product. So it's not equivariantly formal. However, its equivariant homology groups only exist in even degree. But its normal homology groups have odd homology. So somehow the equivariant homology is only an even degree, but its usual homology does have odd Betty numbers. And this isn't so weird, actually. So you can think of just C star, for instance, with the normal action, that would be such a space. Because the equivariant homology is just single number, it's just a point. But the space itself, it has a Betty one kind of thing. And so this is computing, if we use the equivariant homology for this space. And so now the last thing I want to say is that if I combine this with the Hessenberg paving, I'd get an expression for nabla k of En of xy over 1 minus t. And I get something that looks just like the expansion in terms of the LLTs. But now I have this, but I have a different quasi-symmetric function in place of the unicellular LLT. Everything is exactly the same, except now I have, instead of LLT of y, I have this new function, which we denoted by chi. But the thing is, it doesn't just depend on the dict path anymore. The intersection of this open subset. So with each component in the Hessenberg paving, it doesn't just depend on the Hessenberg variety. It actually depends on both the dict path and a single number, which is always at most the number of trailing east steps, which is to say, it actually depends on a partial dict path. So I have these family of functions, chi of pi comma L, each one of which is a quasi-symmetric function, depending on the data of a partial dict path. And so now I just want to tell you a couple of properties of these things. They have a lot of interesting properties. So the first one, and so maybe now I'll switch to a Maple window. I just want to show you some examples of what these things look like. So let's say I take chi, and I take it with respect to a partial dict path. So this notation is 1 is for north step, 0 for east step. And so this would be the partial dict path, but it goes up twice, once to the right, and then twice up again, then once to the right, and then there's two missing east steps. And so this is the thing that replaces the LLT polynomial. so here's the first interesting property. And so this is why that paper has sign positivity in it. Let's say I take the plathistic substitution of that polynomial. I expand it in the Schur basis. And I have to divide by an overall factor of 1 minus q. There we go. So if I take these new quasi-symmetric functions, which replace the LLT polynomial, and then I do the plathistic transformation, the same one that would convert the LLT polynomial into the chromatic symmetric function, and I expand this in the Schur basis. So there's a couple of things. So the first thing you notice is that so the coefficients, they're polynomials, and all the terms are either positive or negative in each Schur function factor. And so in fact, the sign is the same one that appears in the sign positivity of nabla applied to the Schur functions. So each one of these, so it's a family of symmetric functions, and each one has the property individually that if I that when I expand it in the Schur functions, I get something that has this signed property. And so one of the results from that follow-up paper is that there's a conjecture, which is that if the certain Tor groups vanish on the intersection of this fundamental domain with the Hessenberg paving, so conjecture says that if I look at the Tor groups of that thing and I break each one down as a character of the symmetric group, each irreducible representation can only appear in exactly one Tor I. So there's just one row that it would appear in. And if that's true, then that would imply the positivity conjecture, which was I believe proved by Lower and Warrington. So they proved that using the LLT expansion into Schur comma monomial symmetric functions. And so this is the interpretation of that thing in terms of homology, is that this conjecture about the Tor groups. So so that's the first property. So another one, this is kind of so this is interesting. If I take the chi and I take a dict path that's just north steps followed by all east steps, let's give it let's do 5. And then I do the same thing. So I expand this into Schur basis. I seem to only get hooks. And so in fact, this thing, this is the what this is computing in terms of homology. This is the homology of the complement of a certain hyperplane arrangement. So this is what one usually does when you look at the Orlik-Solomon algebra. They take homology of hyperplane complements in the projectivized version. And so this is one of those things, but if you took the complement, instead of being in projective space, you took it in like a Grassmannian variety. I'm not quite saying enough, but so basically this is sort of a variant of a hyperplane arrangement. And also, if I take this thing and I factorize it, you'll see these kind of terms that you might recognize as 1, 2, 5 kind of thing. And so in these coefficients, you also see things that come up with the sorry, the delta operator at t equals 0. So that's and that's something that also just appears only when you take only north steps and east steps, just all north and then all east. And the delta operator, the thing that's K, is what I was calling L here, which is just the number of missing east steps. So maybe I'll mention one other thing, which I have no idea why it's true, but it appears to be true. So if I do what I just did, I expand this in terms of the Schur functions. Then I divide by 1 minus q to the 5. So I get this thing, you can see it's sign positive. Sorry, sign positive again, as it has to be. But also, you notice it doesn't have every possible Schur function. And so in fact, there's a triangularity property that these chi seem to have with the symmetric functions. So there's first of all, there's too many chi's. It's not a basis. You have one for every partial dict path, not every partition. But there's they span all the symmetric functions, and if you choose certain dict paths, you get smaller ones which make up a basis, and that basis is triangular in the Schur polynomials, conjecturally, but not in the dominance order. It appears to be this strange order where you in which you take the partition and you kind of break it up into numbers like this by kind of flipping. And then you compare the lengths of those edges. And so if you take, so this is a total order on the Young diagrams, and there appears to be smaller version, a subset, one for each partition of those chi's, which span the symmetric functions, and they appear to be triangular in their Schur functions in this very strange order. So let's see, I guess so it's almost 10. So there's maybe a couple other interesting properties that these things have, but so yeah, okay, I think I'll stop there.
Thank you. Let's thank the speaker. That's very interesting. Any questions? Yeah, Brendan?
Yeah, thank you. Very nice talk. So you talked a little bit about how you can get these sort of homological interpretations of your symmetric functions paired with p1 to the n basically by counting cells. So you also have Frobenius images. So would the strategy there geometrically somehow correspond to you want like an SN action either on your space or your cohomology, and you want to compute all the graded dimensions or bigraded dimensions of like the parabolic invariance by counting cells? Like if I want the Frobenius image, is that intuition correct?
Yeah, that's it. So it's yeah, this is kind of yeah, I kind of glossed over it. So it's the homology of the space, and then the statement is that there's two different SN actions on that space. So the one that was the X variable one is in fact the Springer action, also known as the star action, and that is the one that has the property that if you take the anti-invariance of a Young subgroup, then that is the same thing as taking the parabolic parts of the Springer fiber. The second one is this different one, which is called the dot action, or sometimes the monodromy action. And that's one which it's not exactly a space level action. So both, first of all, they're not just the symmetric group, they're the affine Weil group. If I wasn't doing this positive cone thing, it would be the entire thing. And the dot action, it's not quite space level, but the translation part of that is actually space level. The symmetric group part isn't, because it kind of changes the nilpotent matrix for the Springer fiber. It like permutes the things on the diagonal, and so it's very close to being a space level action, but but it isn't. So yeah, so in other words, the X variable one, that's exactly the thing that you say. It's the one that takes the parabolic parts.
And that's how you're getting these combinatorial formulas for the bigraded Frobenius image.
Yeah.
With like Schubert-like ideas, but with parabolic restriction. Okay.
Yeah, except for the fact that, so these automorphism factors, so if I didn't have that, the dot action, there'd be no need for the automorphism, there'd be no automorphism factor. And so, but the dot action acts in a weird way with those cells. So it would just be counting if I didn't care about the dot action. But the really confusing part happens, which is how you compare the dot action with those parabolics. That's where that automorphism thing comes from.
Thank you.
Any other questions?
Oh yeah, I have one. Thank you for the nice talk, and for the chi function for a partial IPAC, is there a linear relations between them? Like,
Oh yeah, there is, yeah, there has to be, because there's more partial Dick
Oh, yeah.
paths than partitions, and there are, but so yeah, another interesting factor, there seems to be they live in a positive, there seems to be a subset which is a basis, and all the others, they're not just linear combinations of those, but they seem to be linear combinations with polynomials in Q with positive coefficients. So they kind of positively span. And those are those things which have that weird sure property. And so, yeah, there's linear relations, there has to be, but they seem to come from, if you choose the right subset, you seem to be able to express all the others in terms of positive combinations.
thank you.
Any other questions? All right. Thank you so much, Eric, for the great 3 lectures.
Thanks, guys.
Thank you. So I'll see you guys next week. Bye. Have a nice day. Good night, Jason.
Bye bye.
Bye.